Hi everyone, welcome to 6.2. We're going to talk about one-to-one functions and inverse functions. The other day in class, we discussed what a one-to-one function is, and the figure 6 on the left is an example of a one-to-one function where each element of x, or the domain, corresponds to some element in the y. Notice that in figure 7, there are places where two x's are going to the same element in y, so that is not one-to-one. One-to-one functions are important because they have inverse functions, and we're going to look at how to find the inverse today. So another way to determine whether a function is one-to-one is to use what's called the horizontal line test. If you're given a graph and you place a horizontal line through it, if it goes through in at most one spot, then it is a one-to-one function, which means it has an inverse. However, if it goes through more than one place, then it's not a one-to-one function and therefore does not have an inverse. So if you look at these graphs, this one right here in the middle is not one-to-one because if I was to draw a horizontal line through it, it would go through more than one location. But what we do in that case is we restrict the domain. So if I was to just look from 0 to infinity, so that portion of the graph, now if I draw a horizontal line through it, it's only going to go through in that one spot right here. So that function, when it's restricted, is one-to-one, and it does have an inverse. Okay, so let's look at inverse functions here. So an important property of one-to-one functions is that corresponding to each x in the domain of f, there's exactly one y in the range of f. Okay, so the y's are not being shared, in other words. One x goes to one y, okay? So the function represented by the correspondence of the range back to the domain, so the range is y, and we're going back to the domain, which would be x, is called the inverse of f. And that's how we denote it. It's f to the negative 1, but we don't read it like that. We read that as f inverse of x. So what happens is the x's and the y's just switch. The domain becomes the range, and the range becomes the domain. So if I take a look at letter A, first I need to determine if it's one-to-one, and we said that, we looked at this the other day and we said, yes, it is one-to-one. So therefore that means that it has an inverse, right? So here in question A, every x corresponds to one y, and every y corresponds to one x. And I'll put, and vice versa. However, in B, if you look at dog and cat, both of those x's go to the same y. So no, that's not one-to-one. Different x values go to the same y value. So as I said, if it's a one-to-one function, it will have an inverse. Okay, so let's look at how to find the inverses. In this first example here, we want to know, does the relation represent a one-to-one function? Okay, and if yes, we want to find the inverse and the domain and range. So how do I know whether it's one-to-one? Well, one x goes to one y. If I look at all my x's, they're all different. -2, -1, 0, and 1. And they all go to different y's. If you would need to look at a mapping of that, it's a visual way of looking at a relation to determine certain things. So I'll put all my x's, my domain, in the left circle, and all my range or y's in the right one. And now if you draw an arrow from each x to its corresponding y, you can see that only one arrow goes from each of the x's to the y's. So there's no shared x's, there's no shared y's. So yes, this is a one-to-one function, okay? So as we said, the domain here would just be -2, -1, 0, and 1. And the range are your y's, which would be 6, 3, 2, and 5. Okay, I already created the mapping, so I'm just going to move this here. Okay, and we said, yes, it is one-to-one. So to find the inverse, right, this would be S inverse. All I'm going to do now is take my domain and range and switch them. So in that first order pair, it's -2, 6. Now it just becomes 6, -2. And the second order pair becomes 3, -1, and so on. So it's that easy. All you're doing is switching the x's and the y's. So there's an important property of inverse functions when you graph them. The graph of a one-to-one function and the graph of its inverse are symmetric with the line y equals x. So y equals x is this line right here. And when we say it's symmetric to it, the blue and the red graphs will match up with each other if you were to fold along that orange line. So in this example, I'm given a graph and I want to find f inverse using the function f that's given, okay? So to find f inverse, if I know that property, that function is going to reflect off the line y equals x, let's first graph y equals x. So y equals x, remember, is just a line that passes through 0, 0, and it goes up 1 over 1. And down 1, left 1. That's the line y equals x. Okay, and I'm going to draw a dashed line. And you're going to see when we graph f inverse, it's going to reflect over that line. Okay, so to reflect over y equals x, all you're going to do is switch your x and your y in your ordered pair. So for example, xy becomes yx, which should look familiar to you. That's what we do to find an inverse. So if I take my first point, right, this one, let's go with this top one right here. That's the point 2, 1, 2, 3, 4, 5. To graph the inverse, I'm just going to switch it around and it's going to become 5, 2. So now when I graph 5, 2, that point right there, you can see that these are the same distance from the line. If I was to fold along that red dashed line, those 2 points would map onto each other. Okay, if I take this next point, 2, 1, and find its inverse, it just becomes 1, 2. Oh, sorry, it was 1, 2. If I want to switch it around, it becomes 2, 1. So 2, 1. And then this point over here in the second quadrant, that's -2, 1. So that's just going to become 1, -2. And then the last point down near the letter F, that's 1, -3, -2. So that's going to become -2, -3. And then now all you have to do is just connect. And you'll have f inverse. And we'll label it f to the -1, which again, remember, means f inverse. One way to verify that functions are inverses of each other is to determine whether the range and domain switched, okay? And we learned from graphing above that the function will always reflect over the line y equals x, and then you have the inverse function. So what we need to do is we need to take our equations and we need to be sure that they both simplify to x, which is the line that the graphs will reflect over. So what's important to remember here is that when you replace f of x with f inverse, that you want x for your answer. And when you replace f inverse for f, you also should be getting x for your answer. So let me show you. So we want to verify that these two functions here are actually inverses of each other. So the first thing I want to do is find f inverse of f of x, right? So we're doing a composition, which is what we learned the other day. So what I need to do is take f of x and put it inside of f inverse. So f inverse is one over x minus 1. And wherever there's an x, I'm going to replace it with f of x. So you can see now, all I did was I took my f of x function and put it where the x is. That's all I did. And now you want to simplify that and make sure that it equals x. So to simplify this, we're going to, remember yesterday we kind of encountered this problem where we had a denominator. So what I need to do is just multiply the top and bottom by x plus 1. Okay, and when I do that, when I multiply the numerator by that, I'm going to have x plus 1 and then minus x plus 1. And then in the denominator, I'm going to have, when I distribute this, x plus 1, they're just going to go away, and all you'll be left with is 1. So in this part, we're going to look at how to verify an inverse function. And so when I do this now, we just looked at a graph, and to graph the inverse, we knew that it reflected over the line y equals x. So if we want to verify whether a function and another function are inverses of each other, you want to check two things. You want to look at the composition, which is something we talked about in one of the other lectures. Here you're looking at f inverse of f of x should equal x, and f of f inverse of x should also equal x. So I'm doing two compositions, and I'm just showing that both of them equal the reflection line x. So for this first one, I'm going to first do f inverse of f of x. So I'm just taking f of x and replacing it inside f inverse. So if I write down f inverse, wherever there's an x, I'm going to replace it with f of x. So I'm going to replace this x down here in the denominator with f of x, which is 1 over x plus 1. Now I need to show that that simplifies to x. So if you focus on just the fraction here, that's called a complex fraction. 1 divided by 1 over x plus 1 is really just 1 times the reciprocal of 1 over x plus 1. So it's really just 1 times x plus 1. That's all that yellow part simplifies to. It's a division problem. And when you divide fractions, you just skip, flip, multiply. So 1 times x plus 1 is just x plus 1. And then the 1 and the negative 1 cancel, and you're left with x. And that's a good thing. You want the composition to equal x. Now we're going to check and make sure, though, that f of f inverse of x also equals x. So now I'm taking f inverse and plugging it into f. So f of x is just 1 over x plus 1. So again, in place of x, I'm substituting 1 over x minus 1. And here, the negative 1 and positive 1 cancel, and you're left with 1 over x, which again is a division problem. It's just saying 1 divided by 1 over x, which is just 1 times the reciprocal. So since both of these compositions equaled x, f of x, so therefore f of x and f inverse of x are inverses because both of their compositions equaled x. We can also find inverses of functions defined by equations. So if you think back, an equation is just another way to represent a function. And when we were finding inverses, all we did was switch the x and the y. And that's all we're going to do here. When you're given an equation and you have to find an inverse, you're going to first switch x and y. And then second, you're going to solve for y. So I'm going to make f of x, x, and x turns to y. And then now all I'm going to do is solve for y. So I'm going to subtract 1. And I get x minus 1 equals negative 3y. And then I'm going to divide by negative 3. So your final answer is going to be y equals x minus 1 over negative 3. And I'm just going to turn that y into f inverse of x. Another way you can write your answer, though, you can split that fraction apart and make it 1 over negative 3x. And then negative 1 divided by negative 3 is just positive 1/3. So that's another way to write your answer. You can also, if we look at this one, f of x is the same thing as y. So I'm going to replace f of x with x and make the x the y. So it's x equals y cubed plus 1. And then we're going to solve for y. So I'm going to subtract 1. And if you think back, like, how do I undo a square if I had y squared? I would take the square root. How do I undo a cubed then? I just take the cubed root. And what happens is the 3's will cancel each other here. So all you're left with is the cubed root of x minus 1, and we're going to make this f inverse of x. So if we take a look at the pictures, right, we can again see that they're going to be inverses of each other because they should reflect over the line y equals x. So I already have it typed into Desmos, and as you can see here, both of those equations, x cubed plus 1, and then the cubed root of x minus 1, they are symmetric to each other through the line y equals x. So if I fold along that dashed line, the green curve, which is x cubed plus 1, and the blue curve, which is the cubed root of x minus 1, will map onto each other. You all can try the last example there. I'll give you the answer. Remember, you're going to switch x and y, so it's going to look something like this. And then you're going to solve for y, and you're going to have two issues. One of them is that there's going to be two y's, so you have to narrow it down to 1. The other problem is that you have a y in the denominator, so you have to move it somehow. But the answer you should get for your inverse is going to be x plus 1 over x minus 2. In the last example, we're using a table to evaluate functions and inverse functions. So in this first one, by the way, there's a typo. This should be g of x. In the first one, it's telling us find g of 4. So all I need to do is just go to the x row in the g of x table, and x is 4. What's the corresponding y value? It's 2. But now for letter B, I'm finding f inverse of 3. So remember that an F inverse is really just an F of y, and it's giving us x because they're switching spots. So I need to look at the y row now. So where's y3? Right here. And what's the corresponding x value? 1. For letter C, I'm doing a composition. So remember, this just simplifies to f of g of 2. So I need to first find g of 2. So if I look at the g table, g of x, when g is 2, we get 1. So now I'm going to replace that g of 2 with 1, and I'm finding f of 1. So if I look at the f of x column where x is 1, you get 3 for your answer. For the last one, I'm doing something very similar, but this time I'm finding f of g inverse of 5. So remember, this is actually going to be your y value. So when y is 5, what's x? It's 3. So g inverse of 5 is actually equal to 3. And now I'm going to replace g inverse of 5 with 3 and find f of 3. So if I go to the f of x table, when x is 3, y is 2. And that's it for section 6.2. If you have any questions, please let me know. But please practice with your homework and practice with any extra problems that you might need to do to feel comfortable with the material. Hope you all enjoy the rest of your day.